So we are busy diluting acids or bases, and we are as well calculating the pH.
Yes.
Sorry, it's a small p and a capital H.
Doesn't matter.
Yes, it does matter. Okay. And we are busy with our first example. We already had a and sulfuric acid solution with a concentration of what? Was it 15.31 mole per cubic decimeter? All right. The pH of this solution we calculated, and we got it as a negative value, and you've never heard of negative pHs before. It just means that that solution's got an extremely high number of oxonium ions or hydrogen ions, protons. Okay.
Ma'am,
Yes.
is there like something like in the lab, not the lab, but like in the story that has a negative pH?
Yeah, the sulfuric acid that I used the other day to dilute, to pour into the water, so that you saw that boiling effect. That is very close to 100% sulfuric acid. So we want to take the solution. Can you remember what the volume of the solution was?
100 milliliters.
So this is my crooked way of drawing a volumetric flask. And the volumetric flask has a little engravement on the neck of it that tells you if the liquid is up to that, the solution is up to that level, it is 100 milliliters, which is same as 100 cubic centimeters. We've got the concentration of the acid in here. Do we have the number of moles in here? No, we didn't calculate it. Okay. Let's dilute the solution. Let's take some of this solution and make another solution. So what you do is you take a pipette. Let's take a 25 mole pipette. So we are going to suck up 25 moles of that acid solution and pour it in a bigger volumetric flask. Let's say it is written 500 cubic centimeters on there. This thing also has a marking. So the 25 goes from the pipette in there, and then we add some distilled water. To make a volume, the volume up to 500. Yes. So you're diluting the solution of sulfuric acid. Number one, let's calculate the concentration of the new solution. Please look, you can copy later. You need to understand what's going on.
So you're taking 25 milliliters from the volumetric mask and taking it to the 500 cubic centimeter one.
Yes, yes. Now it's all about moles. Okay? It's all about moles. How many moles of sulfuric acid am I removing?
0.025. Oh no, sorry.
How many moles of the acid are you removing? Because if you know how many moles you're removing, you know how many moles you are putting in there. That would be the moles that you place in here. Okay? How can I get the moles?
N equals. No, we need to use volume.
We've got concentration, love. We've got the concentration and we've got the volume. How can we get moles? Please see it growing before you just copy. The moles is C times V. Wait, please. Wait. So this is 15.31 times, and what's this volume? 0,025. So this is the moles that you're removing, that you're taking out. What is it?
0.3.
What is this? 0,0?
0.38275.
275.
Yes. Must be accurate.
So 383 then.
Yes.
Okay, mole. Where did these moles go? Into the pipette and then into the 500 cubic centimeter volumetric flask.
Yes.
Do we have enough information to calculate the concentration of the new solution?
Yes.
We do.
Yes.
So concentration is the moles over the volume, and that means 0.38275 divided by 0,5. So what is the concentration of this sulfuric acid solution?
0.7655.
0,7655.
Why are we doing so many?
Yeah, ma'am, why can't we just round it
We're being accurate, man.
off?
No,
Ma'am, can't we rounding it off like at a later stage?
You can round it off to 2 decimals. I have no problem with that. I'm just using the way you are telling me. You are welcome to round it off.
Use scientific notation.
Ma'am?
That is not the argument. The argument is, can you follow the reasoning of how to dilute a solution, the process of diluting a solution? You're not listening. So the concentration of the diluted solution is less than the concentration of the original acid solution. Okay? Please listen carefully now, because here we've done 2 calculations separated from each other. Can I show you that you can do it much quicker?
Yes. No.
The moles that you take out of the first solution, these moles that you take out of the first solution, would be equal to the moles that you put into the second solution. So this is the second solution's concentration and volume, but the N for the second solution is the same as the N for the first solution. So technically, if you understand what you are doing, you can say C2 V2 equals C1 V1 and do the calculation like that. Yes.
And couldn't you also have said C2 is equal to C1 V1 over V2?
Yes, of course, the mathematics behind it is correct. So we calculate C2, we've got V2 is 0.5, we've got C1 is 15.31, and we've got V1 is 0,
So, ma'am, because we dilute the strong
0.025.
acid, we decrease its pH.
Wait, we're getting to the pH point.
Ma'am?
So C2 would be the 0.77. If you want to round it off, I have no problem with that. I will not penalize you. 0.655 mole per cubic decimeter. Tina.
So the 100 cubic centimeters instead of the volumetric flask was just there to confuse us.
No, it wasn't there to confuse you. It is the original solution. And you take only 25 milliliters from the original solution to dilute.
So we won't use the 100 cubic.
You could, but in this situation, I said, let's use only 25 milliliters from it. So the rest of it is still there. But the question could ask you to dilute the 100 cubic centimeters to 500.
Into 500 cubic.
But then you use those values. All right? Now the pH. Must I give you a chance to copy this?
Yes.
Please hurry up. Once we've got the concentration of the diluted solution, we can calculate the pH. But there is a snag, because sulfuric acid is diprotic and it is a strong acid. It will give 2 protons. So what is the concentration of the hydrogen ions in the solution?
2 times 0.
It is twice 0.7655. What do we get there?
1,531. So you can just see it from the mole ratio.
Yeah, mole ratio. Then we can calculate the pH. It is negative log. Now I'm going to deliberately say concentration of H3O+, but you should not be confused by that. Because the hydrogen, no, you should not. Because the hydrogen ion grabs the water, so it forms a dative covalent bond with the water. So the oxonium ion and the hydrogen ion represents exactly the same thing.
So can you just say H3 if you want to?
No, you can't say H3. It's H3O+.
Why do you use negative log?
You just think that the value of
The mathematics behind it you can discover in grade 12 maths. I don't know.
Negative 0.185.
So it's negative log the 1.531. And that gives us
Negative 0.185.
Negative 0.19.
negative
185.
0.185.
That's the most
2 times 0.45.
accurate one.
So it's still negative. So I want it positive, I need to dilute it further.
Yes.
Alright. We're not going to do that.
Do you want to double it to give it to the next person?
But it changed from negative what?
1.49.
Okay, to this.
Almost.
Mfihlakalo, I think they're using the negative log so that they will get a positive answer. Because your concentrations are very small. They are 10 to the power minus something. To get a negative, if you don't get the negative, use the negative log, you'll get a negative answer for pH values, where you should be getting a positive value.
Why not 10? Why not 7?
No, Mfihlakalo, that is not to be answered in the scope of this syllabus. No. No. Right. Okay. Second example. Reminder to staff to please.
Can we do a base?
So the first one, 0,9.
Yes.
So in the first one, pH is equal to negative log the concentration of the hydrogen ions, and for the concentration of HNO3 to be 0,125, the concentration of the hydrogen ion concentration, hydrogen ions would be 0.125 mole per cubic decimeter. So this is negative log 0.125, and that gives us 0,9.
Doesn't that mean P is the same?
Pardon?
No.
It's dissociation.
It's the same concentration.
Please give me the opportunity to explain B to you from the start. Can A's answer disappear?
Yes.
Okay. Now B is a base, and the pH refers to the concentration of the hydrogen ions. So the concentration of the oxonium, or the hydrogen ions, is the same as the concentration of the oxonium ions, but here we have hydroxide ions mixed with the water. Now just to take you back a few steps, Kw is the concentration of the hydrogen ions times the concentration of the hydroxide ions, and this we know is 10 to the minus 14. And in a neutral solution, the concentration of the hydrogens would be 10 to the negative 7. And in a neutral solution, the concentration of the hydroxides will be 10 to the negative 7 as well. Sorry for me. 10 to the negative 7. But now, once you add the hydroxide to the water, the concentration of the hydroxide ions changes. The concentration of the hydroxide ions changes to what? If the concentration of the NaOH is 0,125, what is the concentration of the hydroxide ions? Yes, because it's got one hydroxide for every one sodium hydroxide. So that is 0.125 mole per cubic decimeter. So in this solution of water, once you add the sodium hydroxide, the concentration of the hydrogen ions won't be 10 to the minus 7 anymore, and the concentration of the the hydroxide ions is not 10 to the minus 7 anymore. So we need to, if we want to calculate pH, we need to recalculate the concentration of the hydrogen ions after adding the hydroxides to the water. Wait. So this remains the concentration of the hydrogen. Now in water, the concentration of the hydroxide is 10 to the minus 7 mole per cubic decimeter. What will happen if you add these two numbers, the hydroxides from the sodium hydroxide to the hydroxides from the water? What will the concentration of the hydroxides be if you add 0,125 and 10 to the minus 7?
Same.
Okay, so the concentration of the hydroxide that comes from the water is insignificant, doesn't affect the concentration of the hydroxides from the sodium hydroxide. You agree? Okay. So this concentration is 0.125. Accepted. Because adding a 10 millionth of the hydroxides to 0.125 is not going to change 0.125. Watch the video. So what is the concentration of the hydroxides now? Okay, and what's the concentration of the hydrogen ions now?
8 times 10 to the negative
10 to the negative 14 divided by
0.125.
0.125, which gives us
8 times 10 to the negative 14.
Ma'am?
I'm listening.
Why is it 10 to the minus 14?
You're trying to
It's what they found.
Yes, ma'am, I know you're trying to figure out age, but then, ma'am, didn't we just say
Okay, let me explain again. This is the ionization constant for water. That is a fixed number. The first time they found it, and they did the experiments over and over with water, they found that at the same temperature it is 10 to the minus 14. It stays 10 to the minus 14. No, the concentration in water, the concentration of hydrogen ions is 10 to the minus 7. And in water, the concentration of hydroxide ions is 10 to the minus 7. That's where the 10 to the minus 14 comes from. But now you have added sodium hydroxide to the water. What's the new concentration of the hydroxides? 0.125.
Okay, ma'am, sorry, I just thought it was initially 10 to the minus 7 and you changed it to 10 to the minus 7.
No, the product of 10 to the minus 7 and 10 to the minus 7 is 10 to the minus 14.
You said that the hydroxide ion, right, it's normally 10 to the minus 7
In water.
in water.
Mm.
But now because but ma'am,
You add sodium hydroxide to the water.
is it because sodium hydroxide is a base?
Yes.
So if it was an acid, we wouldn't be doing all of this.
No, the acid ones are easy ones because pH and the concentration of hydrogen is related.
Okay, so if you're adding a base to water, the concentration would change, so therefore you'd have to calculate the concentration.
Yes.
Okay.
Okay. The concentration of the hydrogen ions. So we see that the concentration of the hydrogen ions now in this solution is much smaller than 10 to the minus 7 in water. In water it was 10 to the minus 7. Okay? Now, what is the pH of this solution of sodium hydroxide? Negative log. Concentration of the hydrogen ions, which is negative log of 8 10 to the minus 14.
Now,
Big number.
are these equations given on the
Data sheet, yes.
So the smaller the concentration, the higher pH.
Yes. So if you have a base, the concentration of the hydrogen ions are much smaller, so the pH is higher. So if you did not use negative log concentration, you would get negative answers here. So your pH scale would be a negative scale. So I think the mathematics, the reasoning behind it is much deeper than I understand and know. So they want a positive pH scale. Unfortunately for the examples we chose to do with that sulfuric acid and with the nitric acid, the pH was actually pushing below 0. But we say pH ranges from 0 to 40. I can't teach you everything in the high school syllabus. If you want to learn more about chemistry, you go to university. I want to follow the path of pOH. Now, to introduce pOH to you, pOH. Okay. When you have only water, the concentration of the hydrogen ion is 10 to the minus 7. And yesterday I explained to you where the pH of 7 comes from. Sorry, give me a chance, please. So pH is negative log the concentration of the hydrogen ion, which is negative log the 10 to the minus 7. Watch the brackets changing from square brackets to round brackets, is 7. Now pOH is the ability to form hydroxide ions. In water, what is the pOH? It would be negative log the concentration of the hydroxide ions. So it is negative log 10 to the negative 7 in water, and that would be 7. So when you have a neutral, when you have only water, the pH and the pOH is equal. Okay, wait, yes, only water, in water. Okay, what is negative log of 10 to the minus 14?
14.
That is 14. So can I say therefore that the pH and the pOH is 14?
Yes.
Okay. So I'm going to show you how to calculate the pH with pOH now. The push of the hydroxide ion.
I thought that's the pH.
No, that's the push of the hydrogen ion. So the push of the hydrogen ion plus the push of the hydroxide ion is 14. So I want to show you how to use the pOH plus pH equation to calculate pH of a basic solution. So we've got our sodium hydroxide solution with a concentration of 0.125. What is the pOH of the basic solution? So it's negative log 0.125, which gives us 0.9. So the pOH is 0.9. What will the pH be? So pH is 13.1. The 14 minus 0.9 is 13.1. Is it the same answer as we got when we calculated the pH in the other way? So it's two ways of doing the same calculation. You choose the one that you are more comfortable with when you answer questions.
So, ma'am, does that mean that lower the pOH, the more basic it is?
Yes. But we don't use the pOH scale. We refer to the pH scale.